Welcome to another EE301 lecture. Today we'll be talking about parallel circuits. Starting with the basics, using the same analogy as we did with series, we discuss water as a way to understand conceptually what's going on with the electrons as they flow through our circuit. Again, we have the same setup: a reservoir filled with water, a pump shown in red, and two water wheels shown in green. In this case, we have two water wheels instead of just the one, and they are aligned in what's called a parallel configuration. What that means is that the water, which again gets sucked up through the pump, and in doing so, the pump creates a higher pressure in the water that passes through it, yielding a higher energy. That higher energy water is then given a choice. It can flow down one path through one of the wheels, or another path through the other wheel. But ultimately, the water will always end up in the same place, back in the reservoir. The wheels again represent resistors as before, and the pump again represents a battery. Only in this case, the fact that the flow has two potential paths to travel down is the concept of parallel flow paths that we'll be discussing in greater detail today. In a parallel circuit, you have some sort of voltage source, in this case a battery. Again, conductors that allow for the flow of electrons, and resistors, or other components for that matter, which are arranged in such a way that the current reaches a point called a node where it has a choice. Is it going to turn right and flow this way, or keep going and flow this way? That branching off at the node is what distinguishes parallel paths from series counterparts. You'll note that in our drawing on the left, that all the water up here in the top part of our pipes is at the same energy level. In a basic physics class, they all have the same height, therefore the same energy based on the gravitational potential they experience. So you can say that at this point, the water is at the same level as this point. And we also know that, again, based on gravity, when that water has passed through its respective water wheel, it's down to a 0 point all the way at the base. So the drop in energy from here to here is going to be the same no matter which water wheel it goes through. Even if one of the water wheels is much larger than the other one, the potential difference across the water wheels is going to be exactly the same because the starting point and the ending point are identical. In an electrical sense, what that's referring to is the fact that our voltage drop across each of these resistors, V1 and V2, are going to be the same. And not only that, but in this drawing we have here, it's also the same as the battery voltage. That's because, and we'll talk in more detail about this later, all of these resistors and the battery share a common node at the top and a common node at the bottom. In your home, parallel wiring is what's used to ensure that in all of your sockets you have the same voltage output. If in your house you had elements wired in series and current were to flow in this direction, you would have a lowering voltage from this element to this element to this element to this element, such that depending on the order in which your appliances were plugged in, they would all experience different voltages. This is why a parallel home wiring system is used throughout the country and the world. You need a little more detail here. We see that when we combine series and parallel, it's a little easier to understand some new terms. So we start off with our basic DC source, which has a resistor in series with it, followed by, in this example, two more resistors, these two in parallel. These two resistors are in parallel with one another, and this resistor is in series with the combined two in parallel. More on that later. Also in this example, we notice that, as discussed before, we have several different nodes, nodes being points at which various components touch one another via their conductors. We note that this point here, because it's conducted, or it's connected via conductor to this point here and this point here, that all three of these components share a common node right here. This we'll call node B. Over here, this side of the component and this side of our DC source also share a common node. We'll call this node A. This side of this resistor, this side of this resistor, and the negative side of our DC source also all are connected to the same conducting material. Therefore, they all share a common node, which we call node C. Again, these are all nodes. At each node, current can flow in various directions. For example, at node B, current can flow this way, current can flow this way, and current comes in this way. If I were to redraw node B, it would look something like this, where we have current flowing in and two paths flowing out. These paths are also sometimes called branches. And as stated before, the resistors and the DC source we refer to as components. This terminology will be important going forward, so make sure you recognize what's being discussed when it's brought up. Next, we'll talk about Kirchhoff's current law, KCL. You recall from the last lecture, we learned about Kirchhoff's voltage law. This one will be similar, but we'll deal more specifically with parallel by series, which is more applicable to KVL. Kirchhoff's current law states that the algebraic sum of the currents entering and leaving a node is 0. Now, what I'd like to elaborate more on here is that this says entering and leaving. For the sake of simplicity, we'll discuss only leaving when we make our equation so as to not confuse ourselves on direction. That is, we'll set all of the currents as if they were leaving, equate that to 0, and use that to solve. In this branch that we have, on this node with the various branches that we see on the right side here, we can write Kirchhoff's current law in equation form. We set everything equal to 0 because our algebraic sum is going to be equal to 0. And we discussed earlier that we were going to be talking only about those currents leaving. So in order, we note that I1 is actually entering, so we give it a negative sign. I2, we note, is leaving, so we leave it as a positive. I3 is also leaving, positive sign. I4, leaving. I5, entering, negative sign. That's our basic nodal equation via Kirchhoff's current law. When discussing resistors in parallel, sometimes it's easier to determine an equivalent resistance. Just like in the last lecture, if you have a whole bunch of resistors that are in series with one another, one right after the other, it's usually easier to simplify that into one giant resistor. Well, we can do the same thing with resistors in parallel, although our equation is going to look a little bit different. Specifically, and this is on your equation sheet, the equation we use is that our total resistance is going to be equal to 1 over the first resistance plus 1 over R2 plus 1 over Rn. Again, these are all these resistors in parallel with one another that we're discussing right now. And this entire quantity will be under 1. Another way to write this would be just to put a -1 exponent on the right side. In a special case where we only have 2 elements in parallel, so if we didn't have anything over on the right side here, if all we had was R1 and R2, then again, only in this special case where we have 2 resistors in parallel, our equivalent resistance, our total, would be the product of the 2 resistors divided by their sum. And again, that's only for 2 resistors in parallel. To discuss a really quick example, if we said that R1 was 18 ohms, R2 was 9 ohms, and Rn was 6 ohms, using our equation, we would say that our total was equal to 1 over 18 ohms plus 1 over 9 ohms plus 1 over 6 ohms, that quantity to the -1, plug it in your calculator, and it comes out to 3 ohms. Now we'll note that 3 ohms is less than any of the individual resistances that we had above here. And that's a key element to take away from this. When you put resistors in parallel, the total resistance, the equivalent resistance of each of those in parallel is always going to be less than any one individual resistance. One way to think about this is that if these were 3 different roads that a whole bunch of traffic could travel down, having 3 different roads overall is going to reduce the amount of traffic you're going to have versus if you only had access to 1 road. Even if each of those roads is imperfect and has some traffic, it's better than having only 1 road available to you. So your combined resistance is always going to be less than any one individual resistance. Here's a quick example of how we might use our knowledge of resistors in parallel to solve a problem. So if we were trying to figure out what our values were for I2 and I3, that is current 2 and current 3 on this drawing here. First, we would note, and again, independent of everything that's upstream to the left of this drawing, we would note that we can immediately find the voltage drop across this resistor R1. We know that voltage by Ohm's law is just equal to current times resistance. Well, we're given both of those values. We're given that we have 2 amps flowing through that resistor. We know it's a 10 ohm resistor. Therefore, we have a 20 volt drop across R1. We also know, from what we discussed earlier, that the voltage drop across R1 is going to be the same as the voltage drop across R2 and is the same as the voltage drop across R3 because those elements are in parallel. You're going from the same place to the same ending, so you must have the same drop in voltage. So to solve for I2, all we're doing is rearranging Ohm's law and saying that current is equal to voltage across R2 divided by R2. This is just V equals IR rearranged. We know that VR2 is just 20 volts because it's the same as the V, that is the voltage drop across R1. R2 we're given is 40 ohms. And in proper engineering notation, we note that that's 500 milliamps, I2. Same process for solving for I3. Voltage drop across R3 divided by R3. Again, that same 20 volts because everything is in parallel. R3 has a resistance of 100 ohms. So we have 200 milliamps through R3. Now this is a good dummy check for yourself as well. You note that 200 milliamps is quite a bit smaller than 500 and a lot smaller than 2 amps. And that makes sense because we have the highest resistance is going to correspond to the lowest current. The highest current corresponds to the lowest resistance. And of course, the middle corresponds to the middle. But all of them are going to have the same voltage drop across. When dealing with voltage sources in parallel, we'll first recall what happened when we had voltage sources in series. Then we would simply combine them. If you had V1 and V2 in series, would just yield a V total is equal to V1 plus V2. Very easy. In parallel, not the case. We don't combine our voltages. Instead, by placing two voltage sources in parallel, we actually increase the available current. So we'll recall that we increase voltage for two elements in series, and we increase our available current for two voltage sources in parallel. Using this knowledge, engineers can design batteries that have the appropriate voltage for whatever application they may need, but also able to provide sufficient current to power whatever equipment is expected on them. Now we'll talk about the current divider rule. Again, this is somewhat similar to the voltage divider rule when we were discussing series. So in parallel, just like we divided voltage in series, we're dividing current. In this scenario, we have a voltage source, a voltage E, and a number of resistors, R1, R2, all the way out to Rn. And we want to figure out what the current is through only one of those components. In this case, Ix. We only care about the current through resistor X. Well, we have an equation provided for us on our equation sheet that lets us do just that. You'll notice here, I'll blow this equation up here, that our current through component X is again a proportion based on the total current, where the total current is that which comes into the node, right? That current, I total, is what's divided into 4 or more pieces as it passes through each branch or each path. So that becomes the base of our proportion. The fraction by which we multiply is going to have a numerator and denominator, where our total is our numerator and our individual resistance is our denominator. As we discussed earlier, our total resistance is always going to be less than any individual component resistance. Therefore, we know that our current passing through any component X is always going to be less than our total current. In the special case where we only have two elements or two resistors, for example, in parallel, and we wanted to find the current through element number 1, we would use our special equation, where again we're using a proportion of our total current, where we look at the resistance of the other component divided by their sum. You'll note here that the numerator is for component 2 when we're trying to find current 1, and vice versa. The reason for that is because in an extreme case, let's say that Rn were 10,000 ohms, a lot of resistance. Or actually, we won't talk about Rn, we'll talk about R1 and R2. Make it a little bit simpler. We'll ignore the right side of this drawing, and we'll say that we're only considering R1 and R2. So let's say R2 was 10,000 ohms. And R1 was a very small value, just 1 ohm. If we wanted to find I1, it of course is going to be a portion of our I total, where our denominator is going to be the sum of the two of them, always. And our numerator, we can logic this out by saying, well, I know I have a whole lot of resistance down this I2 path, not very much down this I1 path. So I'm pretty sure that my I1 is going to be a large portion of my total current. Sure, some of it's going to travel down the high resistance path, but most is going to go down the low resistance path. So I want my numerator to be a large number. Well, here's my large number, R2. Sometimes it's helpful to think about things in an extreme case if you're not quite understanding where an equation is coming from. Last thing we'll do is an example, the Kirchhoff's current law. In this case on the right, we're given a somewhat strange looking diagram, but one that I'm confident you all can solve if you can just identify the nodes. You'll notice here that if I were to draw my little dots where all of my components end, then I just have one giant node here that connects all of these guys together. That's all one node. Therefore, I can say that each of these resistors is in parallel with one another. Therefore, the voltage drops across each of these resistors is also going to be equal. And not only equal to each other, equal to 270 volts. In order to figure out what the current is through each of these resistors, which is what we're trying to do in this problem, we need to figure out what our equivalent resistance is to identify our total current, which will then yield the individual currents. So our equivalent resistance is just going to be 1 over 5.6 kiloohms plus 1 over 3.9 kiloohms plus 1 over 4.3 kiloohms plus 1 over 2.7 kiloohms, all that to the negative 1. We can't forget our units. And this just comes out to 963 ohms. I total then is just using our V equals IR, Ohm's law equation, is just going to be our V total divided by R equivalent, or R total. I'm using those terms interchangeably here. That's just 270 volts divided by the 963 ohms, which we just solved for, to yield 280 milliamps. If we were then going to solve for any one of these individual currents, say we wanted to find I2, using our Kirchhoff's current law, we would say that 280 milliamps is our total current times our total resistance, 963 ohms, divided by the resistance of the single component we care about. For I2, that's just the 3.9 kiloohm resistor. And we get 69.2 milliamps through current I2. The process would be the same if we were trying to solve for other currents. If I was trying to solve for I3, the rest of this equation would be the same, but my denominator would now be 4.3 kiloohms. Sorry if you can't see that on here. And that comes out to 62.8 milliamps, and so on and so forth. And I could solve for each of my currents, I1, I2, I3, and I4, all the same way using Kirchhoff's current law. And one way to check myself at the very end would be to say all of those currents, which I've calculated using KCL, must sum to 280 milliamps.